Hello everyone, welcome to this webinar, Overview of Floating Offshore Wind. My name is Tiffany Byrne and I will be moderating the webinar. Before I introduce the speaker, I want to cover some logistics to make sure you get the most out of the webinar. Today we have over 500 participants who have registered, therefore it will not be possible to capture all of the questions you may have in real time. As such, all of your lines will be muted. There is a chat feature within your webinar controls that you can use to pose questions throughout the duration of the webinar. We're going to gather all the questions offline and answer them in a written Q&A document, which will be disseminated later with the final presentation document. The webinar audio will also be recorded, and it is our intent to post it with the presentation on YouTube after everything is complete. We will send an email to the webinar registrants with a finalized YouTube webinar link and Q&A document. Now, I would like to start the webinar, which is scheduled to run for about 1 hour. We're right on time. Our speaker today is Walt Musial, who is a principal engineer and leads the offshore wind research platform at the National Renewable Energy Laboratory, also known as NREL, where he has worked for over 31 years. In 2003, Walt initiated the Offshore Wind Energy Research Program at NREL, which focuses on a wide range of industry needs and critical technology challenges. Today, Walt will be providing you with an introduction to the emerging energy field of floating offshore wind. Take it away, Walt.
Thank you, Tiffany. So this is Walt Musial again, and today I'm going to do an overview of floating offshore wind. I want to make sure everybody understands that I'm trying to speak to multiple audiences. I think that this is the intent of this presentation is to reach people who may be familiar with wind power and possibly offshore wind, but maybe haven't seen much at all about floating wind. But if you're new to the field, there's some introductory material that I'm going to cover. And if you're new to the field of wind, there's a little bit of that, but I can't promise that some of the material might be passed. I skipped some of the introductory material just for the sake of time. But so I'm considering this an overview of the new technology of floating, and we'll get right into it. I just put my bio in there. I won't cover that. Tiffany did a great job just now, but if you want to go back to this, it'll be there. I've been working with floating concepts since I've started the offshore wind program, but it's really just starting to take off now. I want to start with this first slide, which is really an introduction to the wind turbine itself. And so let's look at that to start. The wind turbine configuration is a horizontal axis, three-bladed upwind machine. And I'll break that down for a minute. All commercial wind turbines fit this description, except for a few that have been built in the downwind configuration recently. But in general, this is what they look like. The upwind configuration means they face into the wind and the wind passes through the rotor before it passes through the tower. And the wind creates torque, which is the rotational force that spins the low-speed shaft. And we need to turn that torque into electricity. To do that, generally, the land-based machines have a gearbox, which is the cutaway that you're seeing in this picture. The gearbox speeds up that low-speed rotation and directs it into the generator where electricity is produced. So the machines all work this way. There's wires that run down the tower, and then multiple turbines are connected to form what most people know as a wind farm. We also call the wind farm a wind plant or a project. Some of these terms are interchangeable, so if you hear them, don't get too confused. It's just sometimes it's just a matter of where you what you got used to. The generating capacity of the modern utility scale offshore wind farms are now approaching the same scale as conventional coal, natural gas, and nuclear power plants. So we're talking about large scale energy production, all using these turbine configurations. I want to add, though, that offshore wind turbines sometimes have eliminated the gearbox. That's to reduce the part count. So you'll hear or see turbines that are called direct drive machines or direct drive generators. That means the low-speed shaft connects directly to the generator without a gearbox. Those require a lot of technology in the system, in the drivetrain system, but they're now becoming the main one of the main configurations that is used to offshore wind. The first project in the United States was the 30 megawatt Block Island wind farm, and it's shown here in this figure. It's it's comprised of 5 6 megawatt turbines that were originally Alstom machines. It's called the GE Haliade turbines, 6 megawatts each, and it was installed in 2016 off of Block Island. To this date, this is the only wind farm in the United States offshore. The wind plant is, and you can see it in the picture, especially the one to the right, in relationship to where it is in Block Island. These turbines can provide enough power for up to 16,000 homes in Rhode Island. And if you can see the island of Block Island, there aren't 16,000 homes there. So most of this power is used on the mainland. So when they built this wind farm, there was a cable that was brought to the mainland shore of Rhode Island, and it comes ashore at Narragansett and powers most of the power powers the homes in that region. So this is a very small wind farm. It was the first one, and it's still operating, of course. But there's now over 26,000 megawatts of offshore wind that are currently planned in the United States, and this includes, if the way you look at it can be through the regulatory lens in the leasing system, or through the policy lens, in which states have committed specifically to build offshore wind power in their region. And a lot of this is happening, most of this is happening on the East Coast, but it's starting to spread into other areas where we might see floating wind. And this is a floating wind presentation, and I'll get to that in just a minute. So more basics. So how much power does a Block Island wind turbine make? These are 6 megawatt wind turbines. They're big for land-based machines, but today they're actually becoming small in terms of an offshore project. And you can see this picture that was taken in 2016 off a boat, and these are the turbines. One of these turbines would have a power curve that looks like the curve on the right side. This is how all turbines generally look in terms of their ability to produce power, where the wind starts up, and this scale is in meters per second. If you're not used to meters per second, I put the conversion factor at the bottom. So 2.24 miles per hour equals 1 meter per second. So at 3 meters per second, you're roughly 7 miles per hour, where you start to get enough wind to cut in. That's where it starts to ramp up. Now it goes up in a cubic relationship in region 2 of this power curve until it reaches a point around 11 meters per second where you reach rated power. That's the rating on the generator, at which point the turbine can't generate any more power, so it starts to regulate power using the pitch control system throughout the rest of the power curve, and that's called region 3. And that continues regulating power by pitching the blades to feather as they get further and further toward what's called cutout, and that's the 25 meter per second wind speed, at which point that's about 56 miles per hour, at which point there's just not enough times when the wind blows that hard to make it make sense for the turbines to stay on. So we shut the machines down, and then the machines are furled thereon after that, up and through extreme winds. And this site could see hurricane wind speeds, but the machines will be off at that time, and you can see why following this power curve. But so now I've been just talking about offshore fixed bottom machines, and that's what these machines are. You can see those yellow substructures are attached to the bottom of the sea in about 30 meters of water depth. These are called fixed bottom machines. So a floating machine is quite different. but a lot the same. And so this next picture kind of shows some of the parts of the wind turbine that are above the waterline. So a fixed bottom offshore wind turbine and a floating offshore wind turbine might look a lot the same in some, depending on the substructure that's used. And you can see this turbine on the right is actually a floating machine. It looks a lot like the fixed bottom machines because you can't really tell if it's fixed to the bottom. The fixed bottom machines that we use are a lot the same as land-based machines actually, but they're bigger and they have much more complex support structures that have to be installed out in the ocean. And they're designed to withstand the harsh conditions of the marine environment, like corrosion and things that happen, and they have to be maintained in that environment as well. The floating turbines look similar, but the big difference is that they're supported from the bottom by buoyant substructures. Those are moored to the seabed, so they're floating, but they're moored through cables and lines that connect to anchor systems. And before I move on, I want to just clear up a couple things about terminology because people get confused when I refer to the support structures or the, which is also, some people call those the foundations. The substructure is actually a part of the support structure. The substructure is the part that the platform that it's attached to. The support structure includes the platform that it's attached to, as well as all the mooring lines and the anchor system. And some people might call that the foundation, but the foundation is really just the part that attaches it to the ground. So hopefully that terminology will help as we go forward, but I'm using the terminology that the engineers use to design these. So when we're talking about the platform itself, it's the substructure, and the whole thing is called the support structure, which includes the tower, by the way. When we get into the differences between fixed bottom and floating, there's kind of a cutoff line of depth. They're very depth dependent. Almost everything that's been installed so far has been in depths below 60 meters and therefore has been fixed bottom. The new technology that's emerging for floating is really addressing applications where the depth is above 60 meters, and that's shown in this picture. So you see kind of below the waterline, these are artistic views of different types of foundations, different types of substructures. There's the monopile, which is the most common, and then there's the four-legged jacket, which is the kind of substructure that you saw in the Rhode Island, Block Island pictures. And then beyond that are these floating systems, and I'm going to spend more time talking about those in just a minute. Looking at this same picture on the right, if you just stick to the fixed bottom systems, there's 27,000 megawatts installed globally in the fixed bottom type. Of the floating type, there's only 82 megawatts. So 0.3% of the total installed capacity is floating. We're just getting started, people. So that's that's what this slide is really telling you. And so we're excited about the floating industry. The established fixed bottom industry is already going, and I included a few of the leading countries that have installed over a certain number of megawatts. These are the top 7 countries in the world that have installed capacity of offshore wind. But this is all fixed bottom technology. For floating, we're just getting started. So why are we excited about this? It's because 80% of the offshore wind resources in the world that could be feasibly developed are greater than 60 meters, which points to this technology. If we use floating technology, we'll be enabling sites that are further from shore, more out of sight than the fixed bottom systems, and they tend to have better winds. So the economics and the feasibility of floating is in our favor in a lot of these areas. And we're already starting. We already have 82 megawatts installed, but a lot of that is just starting to accelerate right now. And we expect that we'll see floating technology at the utility scale. And by that, I mean 600 megawatts to 1,000 megawatts per project by the year 2024. That's only 4 or 5 years away. Some of the areas that are being considered globally are circled on this map, and you can see it's the west coast of the United States, of course, where we've done a lot of looking already. Some of the East Coast and Great Lakes, areas in Europe that are now moving in that direction, South America, and then Asia. So we are this is going to be a global industry, and we're excited about the possibility of moving and adapting the technology for floating technology. Now, turning back to the United States, we have this is our map of showing two things, and I have to apologize. It's an old map. We're using resource data that is old, and it's no longer developed using the methods that we use today, but it tells my story the way I want to here. You can see the colors represent the good and the excellent resources of the United States, but superimposed on this map is also population densities. And the key point for why are we pursuing offshore wind is the first bullet, which really indicates that the resources match up with where the people live and where the energy gets used. So you can see that the 80% of the population of the U.S. lives near the coast. They live in a state that's adjacent to a coastal, an ocean or a Great Lake, and that makes it a lot easier to build transmission to bring that the resource and convert it to electricity and bring it to where the electricity is used. If you go offshore, you can also see from this map that the resources, the winds are stronger and they're more consistent. And that gives us more energy and easier to achieve the cost goals that we're shooting for. Another benefit is that, especially in populated areas, it's really hard to find large tracts of land to build big solar arrays or big wind power plants. But offshore, it's much easier to cluster a wind farm into a large area, and where it's not seen by people on shore, and bring that power inland. So we can build larger projects. By developing this industry, we're going to create a lot of jobs, and I have at the end I have some targets on that, and it's already revitalizing a lot of the port and coastal manufacturing supply chains that were dormant from the loss of some of the shipping industry and other things that have happened over the years. But some of those facilities do exist, and we'll be upgrading them. Now, you got another resource map. This is the one we actually use, and it's based on wind speed. And so the darker red colors represent the higher wind speeds. And the best sites are obviously where the wind speeds are the strongest, but also where the water is not too deep. So even with floating wind, we don't want to exceed certain depth limits, or at least we're basing our resource assessments on a certain depth limit. And we've set these technology filters to do that. So this map is only showing you wind resources in areas where the water depths are less than 1,000 meters deep, and where the wind speeds are greater than 7 meters per second in velocity. And then there's a few conversions there in case you like to speak in miles per hour or knots. 7 meters per second is 15.7 miles per hour and 13.6 knots. So given these assumptions, the U.S. wind potential is approximately 2 times greater than the U.S. electric energy use. So there's a lot of resource there, and offshore wind can contribute a lot to our total generation portfolio. Of course, it's not the only thing that we'll rely on, but it's something that, especially in coastal communities, we can use to supplement renewable power. I don't have a lot on regulatory, but I do want to show what's happening, and most of this is in the fixed bottom industry. These are maps that cover the regulatory activity in the United States, and most people in the U.S. might be able to recognize that I've sliced out the East Coast and the West Coast and Hawaii here. There's very active leasing going on through the Bureau of Ocean Energy Management, which has regulatory authority over the outer continental shelf, which extends from 3 nautical miles to 200 nautical miles. And over the last approximately 8 years, they have granted 15 lease areas in the United States, which gives the developers who own them exclusive site control of up to 25 gigawatts of development capacity. That's what we typically refer to as the regulatory pipeline. We also have the policy pipeline, which is about the same. It's a little bit more now. BOEM has also identified 13 call areas. Now, a call area is a potential wind energy area that's under public review. It might become a wind energy area, or it might not be, or it might change in its scope or dimensions. We don't know yet, but we haven't counted the call areas in the regulatory pipeline up to this date. There's also another category, which are these unsolicited projects that are applications for additional projects that BOEM has received. And for any reason, a developer can submit an application for a project, but it does still have to go through a regulatory process that includes some attention to whether there's competitive interest in that area. And I don't have a lot more on the regulatory, but that's something maybe for another topic. So in the United States, we have areas where floating might be considered, and this map was drawn in a different way. This was based on our bathymetry, and there's 2 colors here. There's a light kind of aqua color, and there's a dark blue. And the light color indicates areas where our cost techno-economic models predict that fixed bottom technology will be superior. And the dark blue indicates areas where the models indicate that floating might be superior. And you can see there's many areas where floating technology might make more sense. Of course, these boundaries can change and as technology changes, but you can see that if you get north of Boston, north of Massachusetts, the shallow water goes away. If you're on the West Coast, there's virtually no shallow water unless it's really close to shore. And in Hawaii, I would say the same thing. The Great Lakes might stand out as having no deep water, but that's not the case. When we did the resource assessment, we eliminated all the deep water because at the time we did that, the resource for deep water was considered unfeasible for the technology in the Great Lakes at the time, because ice flows and freeze overs in the winter could potentially prevent the current technology from being successful year round. There's been a lot of talk about reassessing that position, and the technology for deep water in those conditions is considered possible by many people. So in the Pacific region, we have kind of a push toward floating, because obviously there's high water depths requiring that technology. In the North Atlantic, we have high demand because there's a scarcity of shallow sites that are already there, and the demand is high. So we'll probably see floating in the North Atlantic. We might see it there first in the United States. And then in the Great Lakes, as I indicated, there's likely to be a push toward floating because visual impacts may require further distances, especially in populated areas. So those are the areas we're looking at. There's certainly arguments for the South Atlantic and the Gulf of Mexico, but both of those regions have lots of shallow water. So from the technology standpoint, we're leaning heavily on the oil and gas experience that helped accelerate the first generation of floating wind turbine prototypes, which is kind of, we're past that point and we're moving toward a pilot stage. But the basic substructures that were used were derived from the oil and gas industry, but we're finding that those criteria that we use to design an oil rig, if you use them alone, they don't result in safe, they can result in safe designs and successful designs, but they can be bulky and expensive. So the next phase is likely to be an optimized engineering approach, which could yield commercial mass-produced utility scale systems. And so we're seeing that right now, and there's a lot of knowledge transfer and job transfer coming in from the oil industry. And you'll see, and if you look, that the oil industry is heavily involved in the early phases of the offshore industry, because a lot of those skills transfer directly. So the characteristics of the basic floating platform types are as follows. You can see this kind of illustration of three different types. They relate to three platform types that get their static stability through different methods. So one is a spar, which has a deep draft, but it achieves its stability through ballast weights that's installed very low. The semi-submersible is a low draft system that has a wide footprint on the water plane where it distributes its buoyancy. And this is challenged by high exposures to waves and structure above the waterline, because a lot of the steel has to be right at the waterline. For a tension leg platform, we see that on the far right, that achieves its static stability through mooring line tension, which has a submerged buoyancy tank. And these can be the lightest weight systems, but the problem with these is they're unstable until you hook up the mooring lines. And they have very high vertical load mooring line capacity. So the anchors have to pull up at about 10 times the force of the other two, the spars or the semi-submersibles. So they all have challenges, and we're finding that as the industry evolves and works toward optimization, that these challenges can be mitigated by hybrids of the various systems, and we're seeing that. So from a surface view, there are two types of platforms that you can see here, or that are shown at least. One's a semi-submersible and one's the spar, and they are shown with just so you can visualize what they look like from the top. You can tell the semi-submersible because you can see the structure. With the spar, not so much. So if you look at this illustration, it shows some of the other pieces now. So I'm going to focus on the non-turbine equipment. We already talked about floating substructures, and the dynamic array cables connecting the turbines create a lot of the infrastructure and cost of the system. And then there's the mooring and anchor systems that connect the platforms to the bottom, and the installation assembly, which is not shown in the drawing, but this is really the equipment that has to be deployed to install all these, and both in the harbors and out at sea. And then there's the substations, both offshore and onshore, the export cable that connects between them, and then there's some costs associated with decommissioning that happens 25 to 30 years after they're installed, because that's their expected design life. So there's about 75% of that capital cost goes into the non-turbine cost. So this figure is showing the breakdown of how those capital costs are distributed, and you can see only about 25% of the cost goes to the turbine. The rest of it's made up of all these other things, including the substructure and the electric infrastructure, the assembly and installation, and so on, insurance. And so focusing on that bigger part of the pie is the best way to lower the system cost or the project cost if we're looking ahead to reduce costs. So I'm just going to go through some parts of the wind farm that we already talked about, just so that we have a kind of a better technical understanding. And the first is the mooring line and anchor configuration systems. there's several different types of anchors, and I've only shown the drag and bedment anchors here, but these mooring lines come down from the system and they connect to the seabed. This is shown at a fairly high depth, but it's showing a kind of a hybrid mooring line where you have synthetic mooring line at the top, which doesn't really have much weight to it, and a chain mooring, which is how a lot of these platforms stabilize because they use the weight of the chain mooring to draw the system down and to stabilize it. And so this is one configuration, but it's an example of how it might look. And for those wondering how, what those lines look like, I put in my colleague Marco standing next to a synthetic mooring line, and you can see how big the diameter is. They're huge lines, and these are this is how we keep the platform from moving around. And now, if we go to the electrical side, these are additional cables that carry the electricity. So all of these dots represent turbines. They're connected together, and they all aggregate at a substation. And from that substation, an export cable brings the power to an onshore substation through fairly high capacity subsea cables. In the array cables, they're smaller, but they're still big, and their voltages are 66 kilovolts. Now this is a new innovation that allows us to lower the cost of the wind plants. The electric cable costs will increase as the turbine spacing increases and decreases with turbine size, because with fewer turbines or larger turbines, you need to connect fewer turbines, and the cable costs go down. But the exact spacing of these turbines is really a trade-off between wake losses that happen in between the turbines and array cable costs. So the larger the spacing, the more cable you need and the more expensive it gets, but you have less energy losses. So other factors also could play a role, such as navigational safety, and this has been brought up in some negotiations earlier among projects that are going in the East Coast. And so this is something that needs to be discussed, and it's not really part of this discussion here. So, but I do want to touch on how turbine spacing is determined and how it might change as projects get bigger. Turbine spacing is based on the rotor diameter. And the rotor diameter is the diameter that the blades sweep as they turn around. So one rotor diameter is on a big GE machine is 220 meters, but to create adequate spacing, the machines have to be somewhere between 6 and 8 diameters apart. I've seen projects that are as low as 4 diameters, maybe up to 10, but typically in between that. And they have to have adequate spacing so that the wind has a chance to replenish itself as it's being propagated downstream, so that the turbines in the back row have wind as well as the turbines in the front row. And so this is an illustration of how an 8 diameter turbine spacing would look. The array is just a representation of a geometric array where the turbine spacing is not to scale, but it shows how that might look in terms of laying out 8D versus 10D. But I guess that's all I'll say about that, except for the fact that when we go from these fixed bottom arrays to floating, we're going to use the same criteria and the same physics results. There's some advantages that we can talk about, but I'm probably not going to get to that today. Another thing that I want to talk about in this next slide is the watch circle. That's really accounting for the fact that these turbines can drift within their station. And that's because the mooring lines have some slack in them, and as the wind blows, the upwind side will become more taut and the downwind side becomes more slack, as shown in the figure, and they drift around in a circle. Well, how big will that circle be? It doesn't. It really depends on the design. It depends on how long the mooring lines are and the water depth and the design of the mooring system and also the turbine size. So, but you can appreciate that the turbines aren't necessarily exactly fixed in space. They can move in actually 6 degrees of freedom as they're anchored to the sea bottom. And that can affect some things, but generally the platform's job is to control that motion and to make sure that the turbines are protected from excessive wave action and things that might damage them or cause additional fatigue. So all these turbines have dynamic array cables. That means that the turbines are moving, as we said, the platforms are moving, and we have to protect that power cable from bending and breaking because of those turbine motions. So there's all kinds of protection systems that are involved in the dynamic array cable to protect the static part of the power cable from seeing all those deflections and motions. They help to isolate the cable from those platform motions. And then those subsea cables can be buried, which they typically are for fixed bottom systems, or if it's really deep, they may just be secured with a mattressing system or some other means. And that's part of the design. They all connect to a substation. Now, I don't have a picture of a floating substation because I don't think there is one that has been built yet. But we're working on the same concept as this one. This is one from the London Array, and it's a fixed bottom substation, but it will look, chances are it will look very similar to this, but it will have dynamic array cables attached to it. And these are under development right now. A big part of floating and a big difference between floating offshore wind and fixed bottom offshore wind are the port and infrastructure requirements. We envision that floating systems will be mostly assembled and constructed at quayside or at a wharf facility, and that means that a lot of the assembly and commissioning will happen there too. That's a good thing because it will avoid a lot of the labor at sea, which is very expensive and can be more dangerous than labor conducted in the harbor. So we need wharf facilities that are adequate, and they need to probably be upgraded or built from the existing ones. We need a navigation channel and wet storage that will allow the tow out of a system with the drafts that are being designed. And most of the platforms that have been designed so far are semi-submersibles because they gravitate toward low draft systems that are easily towed out. We need an upland yard for laydown and storage and staging of the parts. We need cranes that have very high capacities, not just in how much they can lift tonnage, but how high it can go. And then the crews and access for maintenance they don't have to be co-located in the manufacturing ports, and they don't have the same restrictions. A lot of these assembly ports need to have no overhead obstructions, such as bridges, so that the whole assembly can be towed out in one piece. So for floating operations and maintenance, we see there's two categories that I've divided here. One is small repairs, where the turbine will be boarded directly by the maintenance crews through small ships. If it's a major repair, they can be disconnected from the mooring lines and towed into their construction or maintenance facility. So now I want to talk about the path to commercialization, which is something that's underway right now, and it's happening more or less organically in the industry. So the top row here really talks about the prototypes that have already been deployed, and there's several of them. They were mostly funded by research programs worldwide. The first one was the Hywind 1, which is, I think, letter F, which is missing, but it was installed in Norway, but there's been several after that was really to prove the concept of the floating systems. And most of these were very successful and produced the energy that they were expected to produce. But that phase is really over now, and we're really entering a pre-commercial phase, which began a while back. We saw a project in 2017 installed by Statoil, and now it's Equinor. The second project of that scale was a 25 megawatt project called Windfloat Atlantic by Principal Power. And both of those are shown in the photographs that you see on the left. But there's about 14 projects totaling about 229 megawatts that are underway and that are already under construction or have been approved or are about to come online. And that phase of pre-commercial installation is expected to be, complete in the next 3 or 4 years. And I think from that we will see these are really bank financed projects, but with subsidies. From that we will see the emergence of the commercial systems, which are really the utility scale arrays. Some of those are being talked about right now, and we're talking about arrays that are over 400 megawatts in capacity. And around 2024 is where we kind of see that happening. And that's about the same time that we would expect competitive cost competitive with market conditions. And that's kind of the progression that's happening right now. Leading some of this is what I mentioned earlier, these hybrid systems, which will be hybrids of the 3 archetypes that were shown in the earlier picture, where they achieve and they overcome some of the shortcomings of the other platform types by combining features of the different types of platforms. So what's needed is, for example, is a low draft to enter the typical port facilities, but a stable platform that can be deployed on station. And some of these concepts that I'm showing here are already in development and part of the pilot projects that are being deployed in Europe and around the world. Here's a couple examples of these projects, and I don't want to spend a lot of time, but the first project was also Equinor, a 30 megawatt 5-turbine project using Siemens turbines off of Peterhead, Scotland. And there's a picture of one of the turbines from a boat. And this project is operating fantastically, as I understand it. It's achieving capacity factors that are higher than expected. It's doing really well. This is a brand new project, Windfloat Atlantic, that was just installed this year. They produced first power on December 31st. 25 megawatt 3-turbine project near Porto, Portugal. And you can see this turbine being towed out to station. No heavy lift vessels necessary to get this on station. And we're waiting anxiously to see how this one performs. So now I want to talk about cost, and I want to make sure I don't run out of time doing it. So I'm trying not to rush here, but how do we predict the cost of a floating wind turbine, especially when the commercial systems haven't arrived yet? So we've been working this question for many years now, and I'm going to try to explain in a few minutes just how that's done. So only 82 megawatts of floating wind has been installed so far, and there have been no utility scale projects built. We've done some studies to show that at the pilot scale, this is about 1/10 the size of the utility scale, that the costs are at least 3 times higher than what we think the commercial costs will be. And this is true. This would be true for a fixed bottom system or a floating system. It just works out that way because there's a lot of fixed costs that you have to pay for whether the project is big or small. So the cost estimates that we use to get us to the commercial scale costs of floating wind, we rely on the market data that we get for fixed bottom systems to validate our system. We use also the U.S. power purchase agreements that are being negotiated now, and we do analysis on those to see if the European projects and the U.S. projects are in the same ballpark. We also fill gaps. There's a lot of gaps because the fixed bottom systems and the floating systems don't have exactly the same components. So we need to get vendor quotes in the areas where they don't. We use developer information that's provided to us. Sometimes that's proprietary to fill those gaps. And then we run our geospatial techno-economic cost models to generate the cost predictions at different stages of technology development for future years. And then we compare those to inputs that we get from a wide range of industry literature sources that are out there, and everything kind of tends to agree, it seems. If you want to read some of the publications that have been done, I've put a couple in of recent publications. There's a report that we wrote on the cost modeling of floating offshore wind and for the New England Aquaventus concrete semi-submersible that was published just in January this past year. And then there was another report that we did for Oregon. This was sponsored by BOEM to look at the cost of what offshore wind would be at feasible sites in the state of Oregon. And you can access those online. So here's what the auction prices in Europe have been doing over the last 5 years, and it's what's gotten people excited. These prices have come down very rapidly, about a 70% decline, and that's what's creating the motivation for a lot of the policy commitments that are based on the fact that cost and price are related. So why are these prices falling? Big part is because technology is improving. Larger turbines are enabling some of the cost reductions. We're also seeing lower risk because supply chains are maturing and people are just getting more comfortable with the operation of these projects, which are performing as they should be. And through increased competition in the auction process now, we're seeing competition among developers to help bring these projects down. There's other reasons why these prices are falling, but those are kind of the big ones. When we compare power purchase agreements in our analysis in the United States for the early projects that are now coming in right now in the United States, we're not seeing a huge penalty between the European prices and the U.S. prices. And you can see the Vineyard Wind analysis is plotted on this curve, and you can see it's right there in the middle of those data. So this is kind of a simplification of what costs are doing and what our models have been showing. You can see that because fixed bottom and floating share supply chains, turbines and array and export cables, the regulations that we use, the port and infrastructure facilities to a large extent, and the O&M and maintenance can be, they're synergistic with each other, and that's driving floating down along with the fixed bottom costs. You can see in the bar chart that the models are suggesting that we can hit, and this is not an NREL analysis, but the models that 5 cents per kilowatt hour for fixed bottom offshore is feasible globally by 2025. Some of these projects are coming in without subsidies right now. So what does that mean for floating? In our models, by 2030, we think in a lot of the areas where we're deploying or we want to deploy floating offshore wind, that we can get to 6 cents per kilowatt hour, even below that if the wind regime is really high. And so you can see there's a lag of about 5 to 7 years between the fixed and the floating curves. But generally, there's nothing in the floating cost equation that would make floating more expensive. So we expect the floating costs to converge with the fixed bottom wind costs over time. And that will probably happen somewhere just after 2030, according to our models. But others might have more aggressive thinking about that. It's possible that might happen sooner. we'll see. So one of the things that is driving this is large turbines. So I wanted to get to that. This curve shows the expected growth of turbines. We're expecting, we have 12 megawatt turbines in development right now. We expect turbines will get to 15 by 2030. This is like twice as big as the land-based systems, probably even bigger than that. That's conservative. This is being driven by a few different factors. Offshore, there's fewer installation and transportation constraints than there are on land, and so we can do it. But larger turbines lower project costs, and that's a given. We've seen that. We can demonstrate that because it really lowers all of the balance and substation costs that are incurred through the array cables and the O&M, and there's more energy that's produced, and so that is reflected in the cost curves. But fewer turbines are also cheaper to maintain, and what we're seeing, or what we haven't seen, is a hard limit to this turbine growth. But it does take a lot of technology to advance to a larger platform, and so it does take time for us to move through this. I'm not sure how large turbines will get, but we're pretty sure they'll get to 15 megawatts at some point. What does that mean for floating? Right now, floating and fixed use the same turbines, but someday we may see optimization around the turbine itself, and that's yet to be seen. So here's just some photos that courtesy of GE that I'm showing that show these larger turbines are real, and and there's new technology that's enabling these huge machines to be built, and GE expects that this will be commercially available by 2022. But other manufacturers, Siemens has announced larger machines, and they're doing approximately the same thing in the same time frame. So we're going to see the industry offshore jump to these 10 to 12 megawatt turbines very soon. So if you take for comparison, one of these 12 megawatt Haliade-X turbines could power 4,000 to 4,500 average U.S. homes, depending on the wind regime. And so and they may be even saying more, but that's what I calculate, and that's quite a bit for one machine. So finally, I want to talk about economic impacts, and these are the impacts associated with offshore wind. DOE did a study in 2015 that looked at offshore wind, and we estimated that about 80,000 full-time equivalent jobs would be created by 2030 by the offshore wind industry. So economic benefits from jobs is certainly one thing, but there's other synergies that can help other renewables grow, like, for example, solar, which obviously only creates energy when the sun is out. Wind blows can blow 24 hours around the clock. So wind, and sometimes at night, wind is even stronger. So coupling offshore wind with solar might be a match that helps generate even more energy and helps offset the times when solar isn't able to produce power. Offshore wind's also putting power in on the low congestion side of the grid. So offshore wind transmission from the coast can offset congestion that's already building up on the land-based side of the grid. And this has been shown in a couple of different studies, but more work really needs to be done in this area. So key takeaways. I talked about the resources and showed that these resources are very close to population centers. And that means that we're going to generate power where the power is needed and where it's used. 80% of the global resources that are in the offshore wind resources in the world are suited for floating offshore wind. So floating could become a much larger part of the offshore wind industry than fixed bottom in the long term. That's just simply because there's more resources for floating, more geographic areas for us to go to. Floating offshore wind is expected to be deployed at the utility scale, which is up to like a gigawatt scale project at a time by 2024. We're seeing this happen right now. There's a lot of planning that's actually going on right now. There's one project in Korea that I could point to. So this is something that's happening. The cost of the next bullet is that the cost of fixed bottom offshore wind has decreased 70%. A lot of people may not have heard that, but that's now able to compete in some electricity markets without subsidies. And these are some of the European projects are showing that. That may be true for in this country someday as well. But we're also seeing that larger offshore wind turbines have led the way for lower costs. So larger turbines are changing those balance of system costs and lowering them down so that offshore wind can compete on the regular market for electricity. And then we're seeing that the floating costs are because floating is such a nascent industry, those costs are lagging what's already happening in the fixed bottom industry. And we think that those lags will be about 5 to 7 years. But floating will eventually catch up, and that the two curves will converge somewhere in the 5 cent or below per kilowatt hour range. So that means that both floating and fixed bottom offshore wind we expect will be competitive with most forms of energy by 2030 or before. And I think that's my last bit. So thanks for your attention. And as we said in the beginning, your questions will be fielded through the chat line, and we'll post them. We'll answer them formally and then post them as we go. So please ask away.
We will leave the line open for just a little bit longer in the webinar so that you can ask any additional questions that you may have. We do want to thank everybody for their questions and for tuning into the webinar today. And we do look forward to future communications from our audience on floating offshore wind. And just to reiterate, the webinar presentation has been recorded. It will be disseminated to the registrants of the webinar and posted on YouTube along with a formal Q&A document capturing all of the questions asked during the webinar. Thank you for tuning in.